Hey guys, welcome back to Michelle's STEM Journey. I'm Michelle and I'm here today with another AMC Problem of the Week video. This week's video comes from the year 2018, 10B, Problem 18, and it deals with casework. I hope you guys enjoyed this video and let's get started. The problem states 3 young brother-sister pairs from different families need to take a trip in the van. These 6 children will occupy the second and third rows in the van, each of which has 3 seats. To avoid disruptions, siblings may not sit right next to each other in the same row, and no child may sit directly in front of his or her sibling. How many seating arrangements are possible for the trip? So I'm going to label the 3 sibling pairs as A, B, and C. So instead of first worrying about which specific sibling is sitting where, I'm going to focus only on the families first. So let's suppose that a child from family A sits in the leftmost seat of the second row. So this is the second row, this is the third row. And so for example, if A sits here, any child from family A sits here, then it could be A, B, C, or A, C, B. So these are the only 2 possibilities. Okay, I'd rewrote over here. So these are the 2 possibilities. Now let's look at the third row. So for A, B, C, it could be either B, C, A, or C, A, B. And if the second row is A, C, B, then it could be C, B, A, or B, A, C. So this is just to ensure that for each column, there's not any siblings from the same family. So now we look at this, and this gives us 4 family patterns. So this is 1, and then this is 1, this is 1, this is 1. So that's 4. Now this is just focusing on the families though. So if we actually put the children in, each family has 2 distinct siblings. So for family A, there are 2 choices for who sits in that seat. And then same goes for family B and family C. So each family pattern gives 2 times 2 times 2, which is 8 different seatings. Each family has 2 different possibilities. So since there are 4 family patterns, we have 4 times 8, which is 32. Now remember that we started by assuming that family A occupied the leftmost seat in the second row, but the leftmost seat could technically belong to family A, B, or C. So we can multiply 32 by 3 to get 96. So therefore the total number of valid seating arrangements would be 96, which is D. So essentially what I did, just to sum everything up, was I first grouped it by family, and so let's just pretend that family A sat in the leftmost seat, and if A sits in the leftmost seat, we have ABC and ACB, and then corresponding to that, we have a total of 4 different family patterns that satisfy the requirements. And then because for each family there are 2 different siblings to choose from, so we have 2 times 2 times 2, which is 8 different seatings, and then we have 4 of these different pairs right here. So you multiply these seatings by 4 to get 32, and then because any family could be in the leftmost seat, it doesn't just have to be A, so we have 3 different seating arrangements, so we multiplied that by 3 again to get 96.